have page 2 for your chapter 11 study guide. Numbers 19 and 20 are just like the questions from the end of page 1. So if you need a recap on how to do these from the beginning, I recommend you go looking back at particularly number 17. Here I'm kind of assuming you already had the review of how to make your table. When I make my table for number 19, again, we always start off with x and y. Not x and y, x and b to the x power. So for us, again, I always recommend -1, 0, and 1 for x's. This time b is 2. So b to the x, let me actually write 2 to the x instead of b to the x. So 2 to the negative first power. Again, if you have a difficult time seeing that, do it off to the side. 2 to the negative first is the same thing as 1 over 2 to the positive first, which is just 1/2. So it'd be 1/2. 2 to the 0, anything to the 0 power is 1. And then 2 to the first power is 2. Again, I want to point out, so you're always going to have the point 0, 1 in the middle, and your other two numbers will always be reciprocals of each other. Then we have, let's see, if we have x plus 2, that means we're going to subtract 2 from our x's. So -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. Then we're going to take our y values and multiply by a. A is -2. So you're going to multiply everything by -2, which will be, let's see, -1, -2, and -4. And then lastly, we're going to have is plus k, which is +2. -1 plus 2 is 1. -2 plus 2 is 0. -4 plus 2 is -2. So let's go ahead and graph these points. -3, 1, -2, 0. Again, I'm looking at these outside numbers here to make my coordinates. -2, 0, -1, -2. Now, don't try. Most of your curves have been going like this or going up like this. Look at the direction of, where these points are falling. And notice that your curve is kind of going to be in the opposite direction. So let me graph my asymptote first. It's going to be the equation y equals, always related to k. So asymptote is going to be at y equals 2. So if that's my asymptote, look at the direction of your curve of those points. Your curve should look something like this. Domain would be, again, -infinity to infinity every single time. The range, the lowest y value of your range is -infinity, and it's going to go all the way up until +2. Number 20, start with our chart. X, and then again, b is 2, so that'll be x and then 2 to the x power. Same numbers as the last chart, right? 2 to the negative first power is 1/2, 2 to the 0 power is 1, 2 to the first power is 2. Then I'm going to have, if I have x plus 1, that means I'm going to be subtracting 1 from all of my x's, which would be -2, -1, and 0. And then I'm going to multiply by a, which in this case is 5. So that'll be 5/2, and then 5, then 10. And then I'm going to add 2 plus k at the end. So again, if you prefer decimals, that's fine. 2.5 plus 2 will be 4.5 or 9/2. 5 plus 2 is 7. 10 plus 2 is 12. So these outside numbers give us our coordinate points. So that'll be -2, and then about 4.5. -1, 7, and then 0, 12. My asymptote is going to be the line y equals 2. So I know where to level off my curve. My domain will always be -infinity to +infinity in interval notation. And then the range, the smallest y value that I have is going to be 2. The bigger number of my range, the tallest y value or the highest y value, will be positive infinity. So these are the details for that graph. Number 21 says, given the exponential parent function below, sketch the graph of the logarithmic parent function. And the thing to remember is that exponential and logarithmic functions are inverses of one another. So exponential and logarithmic, those are inverses. And as you recall, in order to get the inverse, you switch x and y. So we're literally going to pick like a few points on this curve. So the obvious one that I see is this point 0, 1. So if I switch that x and y, I get 1, 0. So let me graph that point. And then none of the other points are going to be directly on the grid, so just kind of do your best. It looks like 1 and then like 2.7. And if I switch those numbers, I get 2.7, 1. So it's going to be to the right 2.7 and then up 1. And let's pick one more point over to the left side. Even though I know this is going to be an asymptote, let's say it looks like this is the point -4, 0, even though I know it's not touching 0, which would be 0, -4 when I switch those. So essentially, what we're trying to do when we graph that is that this should be a reflection over the line y equals x. Which makes sense, because if the inverse is that I'm switching x and y, then I'm claiming that they are equal to one another, so it's going to flip over that diagonal line. So literally just pick you a few points, switch the x and the y values, and you're just estimating where they are to try to make that reflection curve over that diagonal line. Numbers 22 through 24, I give you some information about logs, and I ask you to evaluate just based on that given information. So again, you're going to be doing these with only the 4-function calculator. You won't be able to use the graphing calculator. So essentially what you need to do is we know the log of 3, we know the log of 14, and we also know that if you have the log of 10 to the x power or something like that, because we know that common base is 10, right? So the log of 10 to the x power is just going to be x every single time. So whatever, because technically it's log base 10 times 10 to the x power. So it's just going to be x. So essentially you want to use the numbers 3, 14, and 10 to rewrite the numbers that are given. So if I have a log of 300,000, I want to rewrite the number 300,000 using these numbers. So obviously I'm going to use 3 and 10, right? So if I go ahead and divide out of 3, I can rewrite this as the log of 3 times 100,000. And then I can rewrite 100,000, so I could say this is the log of 3 times 100,000 is the same thing as 10 to the, I think it's going to be the 5th power, right? If I take 10, so I'll put my decimal place where it would be 10, and then 1, 2, 3, 4. Oops, why am I typing numbers? 1, 2, 3, 4. No, that wouldn't be right. That should be 10 to the 5th power. Because you'd put it there where it's 1. Yeah, so you put it to where your decimal place would be here. And that would end up being 5. 1, 2, 3, 4, 5. So 10 to the 5th power. And guys, if you are unsure of that, again, you do have a 4-function calculator. So do 10 times itself 5 times and make sure you get 100,000. Or just use some logic, right? 10 to the 1st power is 1. Or sorry, is 10. 10 squared is 100. So the number of zeros correspond to your exponent. So since I have 5 zeros, that'll be 10 to the 5th power. And then I can further say, okay, using logarithm rules, this is the same thing as the log of 3 plus the log of 10 to the 5th power. And then you use the approximations. We know the log of 3. It was given to us in the problem. It's going to be 0.4771. And then we know that the log of 10 to the 5th power is 5 using this rule over here. So then when you add those, we get 5.4771 is the approximation. Number 23, I've got the log of 140. So again, I'm trying to use the numbers 3, 4, and 10. 3, 14, and 10. So I can rewrite the log of 140. Obviously, if I factor out that 14, that'll be the log of 14, leaving me with 10. So the log of 14 times 10, which I don't need to rewrite 10 with an exponent because there's already an understood an exponent of 1 there. So then I can say, okay, this is the same thing as the log of 14 plus the log of 10. Well, the log of 14 is given in the problem, 1.1461, plus the log of 10, again, it's an understood first power. Well, the log of 10 to anything is just that exponent. So the log of 10 is going to be 1. And then when I add these, I get about 2.1461. I think 24 is the most challenging out of these three because it's a decimal. So here's the deal. I think the obvious thing to do is break it up into 3 and 10. So when I break it up into the log of 3 times 0. I think the hesitation is to do 0.001. Or maybe even you do the correct number of zeros. And it should be 1. Again, if I'm multiplying that, you can check that in your calculator. Make sure that this, when you multiply 0.0001 times 3, that you get 0.0003. Okay? And then again, using what we know about 0.0001, I can rewrite that as 10 to the. Now here's where the number of zeros does not correspond. Many people were saying that this is 10 to the negative 3rd power. If you want to see, think about what 10 to the negative 3rd power is. That's 1 over 10 to the 3rd power. Well, actually, I'm not even going to confuse you by doing that. Basically, you just need to remember how many times do you need to move your decimal in order to get it behind that first number. So that would be 1, 2, 3, 4. So 0.0001 is actually 10 to the negative 4th power. It's that 4th place behind the decimal. And then using our log rules, this is the same as the log of 3 plus the log of 10 to the negative 4th. We know the log of 3 from the problem is 0.4771. And then the log of 10 to the negative 4th will be plus negative 4. So 0.4771 plus negative 4 will be, oops, I don't know why that erased. There we go. Negative 3.5229. Number 25, what is the common log? The common log is a log with base 10. That's what your calculators understand. So if we have log of A, it is understood that this is a base 10. The natural log is a log with base E. Log with base E, also known as, we use ln. So it would be like log base E of A could just literally be written as the natural log of A. So instead of writing log base E, that's understood as just natural log. So using that idea, I want you to explain why does the natural log of E equal 1? Well, if I rewrite the natural log of E as log base E of E, right, because it's natural log of E, so log base E of E is equal to 1. And then I convert this logarithmic form to an exponential form, then this would be our base is E to the exponent is the first power, and anything to the first power is just itself. So that's why the natural log of E is equal to 1, because the natural log of E is equal to log base E of E. which is 1, which implies that e to the first power is equal to e. So kind of this chain of thought here is why that natural log is equal to 1. Number 28, so this is where your graphing calculator comes back into play. This will be stuff that's on your test on the Friday portion. Compare the balance after 15 years of $7,500 investment earning 8.4% interest compounded continuously to the same investment compounded quarterly. Which investment was more fruitful? By how much? I want to remind you that I'm going to be giving you a formula bank on your test. You just have to know when to use each formula and then what all the variables stand for. So to recap, basically you're going to have, if you go rewatch the video or even look at your notes, this past Monday, I broke down the 4 equations and what they all stood for and when you needed to use each one. So if you're not understanding why I'm choosing the particular equation that I am, go ahead and rewatch that little section to refresh your memory. So number 28 says, compare the balance after 15 years of a $7,500 investment, earning 8.4% interest compounded continuously to the same investment compounded quarterly. Which investment was more fruitful? By how much? So I'm going to go ahead and calculate the continuous compounding first. So hopefully you remember that the formula for continuous compounding interest is A equals P times e to the RT power. So this is going to be A equals P stands for the principal or initial investment, in this case 7,500, times E is not a variable, it's a number, so leave it as is, to the RT. If your rate is 8.4%, then that implies that R, when you plug that in the equation, should be 0.084 times T is 15 years, so 0.084 times 15. Now, you don't have to simplify this. You can type this in the calculator exactly as it is, but if you're nervous about making sure, you get partial credit and making a mistake, then simplify this little by little. Go ahead and type in 0.084 times 15 and simplify, that the exponent should be 1.26. And then typing in 7,500 times e to the 1.26 power is going to be approximately $26,440.66. Again, E is on the division key. So if you hit second and then the division key, and then use your caret to raise that to whatever power you want. Or if you hit second natural log, it inputs E to with a caret for you. So there's the continuous compounding profit. We're comparing that to quarterly compound. Now, anytime you have a compounding n times a year other than continuous, you use the equation A equals P times 1 plus R over N to the NT power. Okay, and the only difference here, we still have our initial investment, so A equals P is still 7,500, times 1 plus, the rate is the same, 0.084. The difference is in. If it's being compounded quarterly, a quarterly investment is compounded 4 times a year, which implies that n is equal to 4. So if I substitute 4 into here, then to the nt power, so n is 4 times time is 15. And again, you can go ahead and simplify a little bit if you'd like. I would do 0.084 divided by 4, get that decimal, then add 1 to it, which would be about 1.021. All to the 4 times 15 is the 60th power. And then plug this into your calculator. You're going to get that A is approximately $26,097.91. So comparing these two profits, if I subtract them, obviously my continuous compounding is more fruitful. Continuous more fruitful by, when you subtract, you should get $342.75. So it doesn't seem significant, but hey, it's free money if all it's doing is sitting there and building you profit. 29. Abby invests the sum of money in a savings account with a fixed annual interest rate of 5.25 compounded 3 times per year. That phrase catches my brain. Compounded 3 times per year. That's going to let us know which equation that we're going to use. Anytime it's anything other than continuous and it's money investments, you're going to be using this equation here. After 12 years, the balance reaches $2,528.47. What was the amount of the initial investment? So if I substitute in what we know, we already know the final profit, or we know the final amount. It reached $2,528.47. So that's A. That's equal to, when it says what is the amount of the initial investment, we are finding P. So I'm going to leave P as a part of my equation. Times 1 plus 5.25% means that the rate is 0.0525. Divided by N is the number of times it was compounded that year, which in this case is 3. All to the NT power. So N is 3 times time is 12 years. So the goal is we're trying to solve for P. So I've got, let's see, $2,528.47 equals P times, if I go ahead and simplify this, 0.0525 divided by 3 is going to be 0.0175, blah, 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 blah. So plus 1 will be 1.0175. All to the 3 times 12 is the 36th power. So you can compute that, right? 1.0175 to the 36th power, and then divide that on both sides in order to get P by itself. So divide your final amount by 1.0175 to the 36th power. When you do this, you should end up with the principal investment as approximately $1,354. And it rounds to be that. So I hope you're calculating with me. If you're just kind of taking my numbers and rolling with it, the reason there are no cents here is because those numbers were 9s, I think, if I recall correctly. And so that when they round all up, it ends up being to the nearest whole number. So $1,354.